Users are not the enemy. That's a catchphrase coined by Angela Sass, one of the founders of the research domain of usable security and privacy. And we've just heard two excellent talks on why we should not have an adversarial position towards the end user and that we should be helping them and creating more usable security technology. I would like to extend this idea and say developers are not the enemy either. And I think this is a really key thing we as a domain need to be focusing on in the near future. And in the course of this talk, I hope I'll be able to convince you of this idea. And to do that, I'll give you a brief introduction on this migration from looking at the end user to looking at the developer. And then I'll dive in deeper into two stories which happened in my own group where we have been focusing on developers. And I use the term developer fairly broadly here to mean anybody who is on the more technical side of things, so people who develop code, but also people who, let's say, configure systems, so administrators or security analysts. So the origins of usable security have, as the last two talks shown, focused on the end user. And a very popular topic is warning messages, and you see one here. And it's filled with all sorts of technical details. And what the end user usually actually sees is probably something more like this. And that is so true. Adrian already mentioned that one of the really big problems is habituation. So users see hundreds of these warnings, and they all look the same. And the likelihood of it being attacked is so incredibly low. So there will be thousands and thousands of false positive warnings for every single true warning. And the reason behind that is also human error. So in 2013, in collaboration with Google, we actually looked at all the certificates the Google crawler could find over a given year. And we found 4.5 million unique certificates, of which 610,000 certificates were bad, i.e., they would cause a user to see a warning message if they visit that site. Now, each of those certificates was installed by a human. And it would be so good if we could help those administrators who are making mistakes there configure their systems in a way that the user do not see false positive warnings. And if we manage to do that, the warning message design problem will become much, much easier because we don't have to differentiate between false and true positives anymore. Another good example of where usable security is very active is passwords. This is still one of the most popular passwords. It's the most popular password in 2015. And of course, trying to get users to pick secure passwords is a very interesting problem. And many strategies exist. So one thing, for instance, which we are looking at is whether passphrases like correct horse battery staple, as suggested by the KCD comic, is actually a better way to create passwords than having these kind of 8 characters and numbers and special symbols and things like that. And that's a very worthwhile field of study because passwords are so important. But if we think about it, the really bad password mistakes aren't done by the end user. They're done by administrators and developers who don't salt and hash their passwords, leading to password database compromises affecting millions of users. So you have a single actor with a lot of technical skill making a small mistake, and that affects millions of users. And it's not hard to see why that happens. What you see here is a tutorial from Stack Overflow on how to store passwords securely using the Bouncy Castle library. And as you can see, there are a lot of technical details to get right, and they do have to be right entirely. And to make matters worse, this actually is now completely outdated. So the first thing you find on Stack Overflow no longer shows you how to do it properly because it's just a couple of years old. And again, if one mistake is made, you might lose the whole thing. This is another wonderful example of a developer making a mistake. This is the code of the Apple goto fail. So you just have one line too many, and suddenly the security goes away entirely. So we do live in an environment where a single small design flaw can have catastrophic incidents for your entire system. So looking at the end user really is only the tip of the iceberg. We need to look at administrators, developers, and security analysts in much more detail and help them create secure systems. And working with developers is incredibly fun. developers are very creative people. If they have a problem, they will find a solution. Sometimes security and safety won't be foremost on their mind. And with that, we'll start with the first story, which kind of played out in my group a couple of years ago, and that's concerning HTTPS and Android. So one of my students was creating an app for our work, and he wanted to use SSL to protect the connection. And actually ran into a problem, which is quite interesting, because the default implementation of Android does do HTTPS validation completely correctly. However, only if you have no special wishes. In our case, my student wanted to work with a self-signed certificate. And that does not work out of the box, so you have to write custom code to enable that. And he did what most developers do when you're confronted with an error message. He turned to Google and asked what to do. And he found a lot of forums covering this problem. And one of the nice quotes was, the question was, I'm getting an error of the type Java X net SSL exception, not trusted server certificate. And then there was a lot of text ranting on how annoying that was, and it kind of ended up with saying, I've spent 40 hours researching and trying to figure out this workaround for this issue. And the answer was a one-line. It was just saying, look at this tutorial. And there was a link to a tutorial, which led to some source code which turned security off entirely. Naturally, that did make the error go away, but it might not have been quite what the developer had intended. And my student continued looking and found lots of code which looked like that. So you'd find tutorials saying, well, you can use this trust manager and the problem will go away. And if you look into the two methods and you see where the security should be happening, there's just a comment saying, do nothing. And that got us thinking. If we as security experts are having a hard time finding code how to do it correctly, how must it be for all the other developers? So we conducted a large-scale analysis and looked at 13,500 popular free apps on Android. And we found thousands of apps containing code which potentially would turn off validation, all based on different kinds of trust managers. And actually, there were only a small number of trust managers which were being used by a lot of apps. Now, some of the names are quite obvious. So the fake trust manager or the dummy trust manager, you pretty much know what you're getting into as a developer if you're using one of those. But other names are a little bit more tricky. So the easy X509 trust manager, the simple trust manager, the open trust manager, all potentially sound like something which is just taking the work away from you and is offering you a simple but still secure solution. However, that wasn't the case. So as I said, we found many, many apps which had potentially unsafe code, but it was just static analysis, so we weren't quite sure if maybe it was just for debug purposes. So we cherry-picked 100 apps and actually tried to attack them and see what happened. And we found 41 apps in our 100 which actually leaked credentials, and we found a whole host of things, everything from credit card details to logins to all of the big services. And these 41 apps had an install base somewhere between 39 and 185 million users. So this is a huge problem. But one of our favorite examples is a popular antivirus app on Android, which updated its signature database via HTTPS GET, and unfortunately didn't do the validation correctly. So that meant that we could potentially go in there and change something. So we tried it out. So we set up a rogue DNS server and created a database and gave the database a signature of our choosing. Entered a checksum and gave the fake database a name, and put it into the network in a way that the app would have to talk to it to get its updates. So when we then start the app, and we trigger the update process manually in this case, but this will, of course, happen automatically as well. So as you see, the update process went through without any error messages, so now we can ask the virus program to scan, and this is now an abbreviated version of the scanning process, and it actually finds a threat, and it found our thing, and we gave the program its own signature. So it's found itself here, and is now asking what we should do. So we said, well, remove. Not quite believing that would work, but to our great surprise, the antivirus program did actually manage to kill itself for us. Now, the developers took this with a good sense of humor and had a fix out within 3 days, so they did react very quickly, better than most other companies we contacted with these problems. But here we have experts. I mean, these really are people who know their stuff. and they still manage to make a mistake. And that is completely normal. We are humans, and we all make mistakes. So now we have kind of the problem down. How do we get to the solution? And this is where I'd like to continue on from Adrian's thought that usable security is a science. And we have a lot of methods with which we can look at these problems. And in this case, we can actually use a very simple one. We conducted a fairly small number of interviews with the developers to figure out what was going on. And we contacted 80 developers roundabouts, and 14 of those agreed to do some interviews with us. And we got a whole range of interesting comments back from them. So we had the novice developers who said things like, this app was one of our first mobile apps. And when we noticed that there were problems with SSL certificate, we just implemented the first solution we found on the internet. So that's exactly the process we just saw. They take a tutorial, and it turns off security. We also had more intermediate developers who said we use self-signed certificates for testing purposes, and the easiest way to make them working is to remove certificate validation. Somehow we must have forgotten to remove that code again when we released our app. And this, again, is a very understandable mistake. You're working under a deadline, you add some code months ago for testing purposes, forget to remove it, and you've destroyed security. But we also had, and this is my favorite example, a really expert developer up to a point. So he actually didn't believe us. He said, when I used Wireshark to look at the traffic, Wireshark said that it's a proper SSL-protected data stream. I could not see any clear text information when I manually inspected the packets. So I really cannot see what the problem here is. So we have a developer who is tech-savvy enough to open Wireshark to see that the communication is SSL-protected, but who, despite our explanations, couldn't understand that it was encrypted, but using our key instead of his. And again, this is a very complex scenario. So this is not really something where we say that's a bad developer. It's just he's having to deal with stuff which is not his area of expertise. And finally, we also had some developers who actually knew that there was a problem and did it for other reasons. So we had a blog reader who said the app accepts all SSL certificates because some users wanted to connect to their blogs with self-signed certs. And because Android does not provide an easy-to-use SSL certificate warning message, it was a lot easier to accept all self-signed certificates. So they knew they were doing something insecure, but they just said it's a cost-effective way of going forward. So after having talked to all the developers, we actually had a wish list. And it wasn't a long one. It was just a couple of points. Working with self-signed certificates was one of the foremost issues. And we sat down and we looked at all the wishes they had. And then we looked at how the Android system actually implemented the SSL validation and found that if we replace the trust manager with a new implementation with more usability features, we can actually affect all the broken apps. So we created a system which allowed developers to do all the things they wanted via configuration instead of coding. And this system actually is capable of retroactively fixing all the broken apps in the 13,500 we looked at. The only thing, 19 apps which additionally had implemented pinning would lose that feature because we completely ignored the old implementation. But updating those to configure pinning would have been, or would be easy. So this is an instance where just talking with 15 developers gave us, 14 developers, gave us enough information to fix all the vulnerabilities found in 13,500 apps. And that's a really good payoff. And we found a solution, so it is really worth looking at it. So that's the first story. The second one is going into an even more highly skilled area, and that's malware analysis. So I have a couple of students who are working in this area a lot. And as you can imagine, this is an area where you really need a lot of technical skill to be working. So if you have a piece of malware, you usually get the binary code. Now, the author of the malware had source code and compiled that into binary, and now you have to use a decompiler to get the code back again so you can analyze it. And that, unfortunately, is a very lossy and messy procedure. So you have kind of control flow graphs, and unfortunately, most normal decompilers will have a lot of go-to statements to kind of go from the binary code to the assembly or the C code. Just as an example, the peer-to-peer sample of the Zeus malware has 1,571 go-tos in roughly 50,000 lines of code. That's roughly one go-to per 32 lines of code. That's a lot to get your head around when you're trying to analyze something which potentially is actually written in a way to make it hard to understand. But even without the goto problem, the code produced by, for instance, Hexrays and IDA Pro is not nice to read. So what you see here is a small snippet of the Cinder malware. Anybody like to hazard a guess as to what we're seeing here? I know I wouldn't, so when I saw this code, it was completely indecipherable to me. So this is actually the domain generation algorithm. So malware often has command and control servers, and this code is there to tell the piece of malware where actually to go. And as you can see, this is not something which is easy to read. So what my students were doing was creating kind of control flow optimization algorithms to get rid of all the go-tos. And that already worked really well, so we kind of finished that project. But then we started talking to the malware analysts who we're working with, and they actually, similar to the Android developers, had a wish list. They said, we have a lot of problems because it's very hard to read the code produced by Hexrays. And we sat down and looked at them and actually figured out there's a lot of stuff we can do automatically to make their lives easier. So the original decompiler which we built was called Dream. And we made an extended version called Dream++, which implemented all the usability improvements we could think of. And the automatic transformation between what we see here and what our compiler does is that. And this is already a lot simpler. And you can see here you have kind of two arrays with characters, and you have a single for loop, and it selects characters based on a seed. And that is something which most computer science students, given a little bit of time, will be able to see. But as Adrian said, usable security is a science. We want to quantify how good things are, and we shouldn't trust our gut instinct. So what we did was, again, we went back to the science and we conducted a user study. And in this case, we actually conducted a quantitative control experiment. So we took 3 decompilers. We took Hexrays as the industry standard. We took our Dream decompiler, which already removed all the go-tos, and then we took the Dream++ decompiler with all our usability extensions. And we had our malware analysts create 6 malware analysis tasks, and we recruited 21 students who had completed our malware bootcamp, and we contacted 9 professional malware analysts and had them complete all 6 tasks and ask questions about what the code did. To ensure that the results were unbiased, we had to do a lot of kind of juggling with the task order. So we counterbalanced all the different decompilers so that each decompiler would be used in the same frequency at all positions in the study. And we counterbalance hard and easy tasks, all in the effort to try and get as scientific and unbiased result as possible. And the results are really good. So here's some comments. So even with our improved Dream decompiler, people were still saying this code is not very nice. So the comment was, the code mostly looked like a straightforward C translation of machine code. Besides a general sense about what is going on, I think I'd rather just see the assembly. However, with our usability improvements, we heard things like, this code looks like it was written by a human, even if many of the variable names are quite generic. But just the named index variable makes the code much easier to read. And the results are really clear. So with the students, we saw that they solved 3 times as many tasks with the Dream++ decompiler than with Hexrays. And even the experts who use Hexrays on a regular basis still solve 1.5 times as many tasks with our usability improved decompiler than with the industry standard. And even nicer, when we asked them how they liked the different decompilers, we got a very clear answer. So with the students you see on the right, we have a clear ladder. They liked Hexrays the least, Dream was better, and they liked Dream++ the most. Now you can see that the malware analysts are a little bit more diverse where it comes to Hexrays versus Dream, and this is actually quite understandable since they are very experienced with Hexrays and don't have as many problems with that. But the way they liked the usability advancements was even more than the students. We're guessing because they actually see how much it would help them in their everyday work. So even though these are probably the highest skilled security people I can think of, the simple usability improvements we found for them were really effective and really appreciated. And that's why I want to say developers are not the enemy. We should be trying to make our lives easier, because any benefit we can offer for people in this room will have trickle-on effects for all the users. And problems we can solve on the system layer don't even have to get through to the end user. And that is something where we can get a lot of benefit with fairly little effort. So if you're developing code, security-relevant code, or if you have products which are targeted at security professionals, do get in touch with usability researchers and have a look what we can do for you to make your world a little safer. And with that, I thank you for your attention.